Hello, everyone. Welcome to week 6 of Logic tutorial. In the agenda for this tutorial is we'll go over 3 proofs from the tutorial sheet. And we'll be looking at proofs 1, 3, and 5. The reason why we're looking at 1, 3, and 5 is because and not the others is because the second one is very similar to the first one, but there's a subtle difference. And I encourage you to try the second one after you do the first one. The fourth one is an extension to the third one. And again, I encourage you to try it after you've sort of understood how Semantic Tableau work. The sixth proof has a very detailed explanation on Waddle. And I encourage you to try it first by yourself and then go on to Waddle, check the solutions, and see if you understand whatever's been explained. After that, we'll do a bit of discussion. We'll end it with a Logic4Fun puzzle, which is the parking lot puzzle. So this is the first proof that we'll be doing. And I just missed a symbol over there. And now we're ready to start proving. So the antecedents are our assumptions, and we say that, let's say that these assumptions are true. That's the first assumption. The second one, the second antecedent, the second one is also true. That's our assumption. And we're saying that we're just assuming that the conclusion is false, which is another assumption that we are making. And we'll see if this goes well for us. If all of the branches are closed, it means that the sequence is valid. Otherwise, if it is open, it just means that it's not valid. So we are trying to expand the branch, expand as many of these as we can first before we branch out. And the very first thing that I want to expand is line 3, where we've got a negation at the very start, and we can just use negation elimination to get rid of it. So because this is false, we just say that this is true, and we are done. By line 3. And now we'll try to expand line 2. The reason why we are doing line 2 before, we are trying to expand line 2 before line 1 is because existential quantifiers usually introduce new objects into proofs and trees in this case, and universal quantifiers such as the FOL symbol, it sort of takes into account all of the objects that were introduced. And we want to make sure that we introduce as many objects as we need before using the universal quantifier. Because otherwise, you would have to use the universal quantifier and then you introduce something new, and then you need to sort of use that universal quantifier again to sort of talk about any new objects that you introduce later. So we just want to get everything done at once, which is why we introduce first and then we use universal quantifier. So let's expand line 2. In this case, I will be just introducing A as the object. You can introduce whatever you want. I prefer going alphabetical because it's very easy to keep track of things. And now we can further expand line 5. Let's just expand one line completely before moving on to the other ones. Sorry. Yep. So 6 and 7 got true, not HA, and I'm not repeating the proof, the explanation for every single line, but I encourage you can sort of do it for every single line, and that just makes it more sort of clear. And now we can expand line 7 because we've got true, not HA, and we can just change that to false HA. Now that we are done expanding line 2, we can expand line 1 next. And since A is our only object, we just need to write this once. If, for example, we introduced B as well, then we'd have to do FA implies HA, and then we would also have to do FB implies HB. But luckily, we do not have to do it for this one. So that's a for all elimination, line 1. So we've got two options now. We can either branch out or we can expand line 3. I would prefer I would prefer expanding, but you can do either, because in this case it works really well that you can just branch out first and then expand, but I'll just do it for the sake of consistency. So I'm expanding line 4, which sort of is built from line 3. Sorry, that's terrible handwriting. And now I'll branch out and sort of branch line 9, which is false, FA, application, explanation, 9, and true HA. But we can see that we have arrived at a contradiction for HA. In line 8, it states that HA is false, but here it says that HA is true. That's not matching, it's a contradiction, and therefore this branch is now closed. So now all we need to do is worry about the left branch, and we should be hopefully able to address this as well. So we've expanded line 9. Now let's expand line 10. So we can see that we've also arrived at a few more contradictions over here. Line 11 over here, FA is false, but 14 says that FA is true. That's contradiction. And we also have line 13, which says GA is false, but line 6 over here, which is sort of built from the initial assumption, is that line GA is true. So that's another contradiction. As a result, all branches are closed, and therefore sequent is valid. Let's move to the next question, which is question 3. Again, here we've got two antecedents and one consequent. Our antecedents will be true. So this is essentially me rewriting the question, but in tree form. That is our first assumption. This is the second assumption. which is true. That's our assumption. And the third assumption is that the conclusion is false, and we are trying to close all of our branches. And if any branch is not closed, it just means that the sequence is not valid. So we have a couple options here, as we can see that the for all the for all quantifier is true for the first two lines, but it's false for the third line. So maybe we can expand the third line first, because we need to introduce an object in this case, and we just do that. We introduce a, so x is equal to a. Yep, that one. This is an instance of 3. And then we have, well, we could either expand 4, or I think we should just expand 4, because we want to complete the third line first. So we're saying that FA is true and GA implies RAA is false. This is instance of 4. And we can also expand line 6 now. So let's say that GA is true, but RAA is false. And just try to recall that this was sort of what we derived in week 4 when we were looking at implication rules for semantic Tableau. So that's instance of 6, and that's implication. Now we can expand maybe line 1, which is, since there's just, since there's just one object, we just talk about A, which is true. This is for line 1. And we can branch out if we want, or we can just expand line 2 as well. So we've got true GA, because A is our only object, not HA, to implication elimination. Now we need to branch. So we are expanding line 9. It's true, yeah, true HA. And we check if we have any contradictions. We do. The first obvious contradiction would be line 5, where we have FA is true, and line 11, where FA is false. That's awesome. The left branch is now closed. For the right one, we need to see that we need to look for a contradiction for HA. We haven't arrived at one yet, so we just keep going. And in this case, we just expand line 10. Oh, sorry. GA, and the 14th line would be true, not HA. We can expand this. This was implication 10, and this will be negation 14. Now we'll look for contradictions, if any. If there's none, then we just say that the sequence is not valid, but let's just check. So here, line 15, HA is false, but line 12, HA is true. So this is a contradiction. Line 13, GA is false, but line 7, GA is true. This is also a contradiction. I guess an important note here would be, I do not think I have a very valid example, but let's just say, suppose we've got false FA here. If we ended up with maybe a hypothetical line 16, which says true FA in here, we would still not be able to arrive at a contradiction with line 11 and 16, with lines 11 and 16, because these are essentially in different branches, and the branch happened at line 10. So we cannot, if even though we get contradictory maybe elements or statements, we cannot just have a contradiction with lines which are not in the same branch. So this entire thing, the unbranched part, is all part of one branch, and then anything lines 12 and 13 are in the same branch, lines 12, 14, 15, same branch, line 11 is in a separate branch. So I'll just get rid of the unnecessary stuff. But essentially now we've proved that the sequence is valid since all branches close. The last proof for this tutorial, this recording, is the fifth one. And here we use existential quantifiers only, and I thought it would be kind of fun to do it. So, okay. So, as always, assumptions first. The conclusion assumption is false, is what we assume. We would have to disprove it using semantic Tableau. Okay, anyway, R, X, Y. This is another assumption that we make. So now what we can do is we can expand line 1. Here we say that we just assume that X is equal to A in this case. So we have and we always need to start from outside to inside. We need to go from outside to inside when we are sort of unwrapping the quantifiers. So this is line 1, instance of line 1. Let's continue. So okay, this is instance of line 3. Now we expand. I think I was supposed to do this. Yeah. Now what we do next would be to expand line 2. Since we've already stated that X is A, we cannot, oh, sorry. I realized I wrote my assumption incorrectly. So this was supposed to be RYX. Since we've already, for the previous one, said that X is equal to A, we cannot go with X is equal to A. We need to pick another object, and for this case, we'll just go with X is equal to B. The goal is to find interpretations that can prove or disprove, essentially close or disclose, close, that can lead to a closed sequence, sorry, a closed tree. So we are essentially just picking with B because we want to get somewhere. We expand line 5 now. Here, since we've already used y is equal to b, I want to use y is equal to a this time. And now we see that we have a contradiction, which is why I didn't use C or D or like any other object, because I wanted to get to a contradiction if possible. There is a contradiction, and as a result, the branch is closed. Since there's no other branches, the tree is closed and the sequent is valid. That's it for the proofs. Let's now move on to the discussion part of this tutorial.
Welcome to the second part of this workshop, where we are using Logic4Fun for checking semantic Tableau. So I'll very quickly read the description, where it says this is less of an exercise and more of an explanation on how you can use Logic4Fun to support you to check your semantic Tableau proofs. Hopefully this also helps you better understand what semantic Tableau does. Semantic Tableau takes a set of formulae and tells you either whether there's no interpretation that makes them all true, and this is quite important because we'll be using this concept a lot. Or it presents you with such an interpretation, but that's exactly what Logic4Fun does. But we'll come back to this in a minute. So we've got this toy question, or maybe like, yeah. So where we've got sorts, which has entity, we've got vocabulary where we have predicate F and predicate G, and we've got some constraints. We've got two true constraints and one false constraint. Essentially, this translates back to there exists X fx for this one because this is true, so it's a premise. Again, this is true, so this is the premise. There exists X for gx, and since this is false, this is the conclusion. There exists X. There exists X for fx and gx. There's also a quick note that I wanted to make, that we could use these true or false labels only to emphasize the approach of semantic Tableau, but you could also just do it without these labels by putting a not in front of the last formula. So essentially what this means is we've got these labels over here. So we've got true, and we've got false over here. What we could also do, if you do not want to use these labels, would be to, for the false statements, just put a not, just wrap a not operator around the entire sequence, and you should be good. So now that we've had a look at the toy question, let's try putting this into Logic4Fun and see what outputs it gives us, because that's the first discussion point. I think I'll have to stop share and reshare. And over here. Okay. So I've like put everything, I've typed everything to save some time. In sorts, we have entity. In vocabulary, we have predicate F and predicate G, both take entity. And we've got constraints over here where we have true sum x fx, true sum x gx, and false sum x fx and gx. So essentially what we're going to do is we're going to hit solve and see what output we get. We get for entity, we get two interpretations for each of F and G, and we also get two models. So over here, oh sorry, I said two interpretations for F and G. I actually meant two objects for F and G. So we've got 0 and we've got 1. We've got false, true, and true false. So we do not see both F and G being true for any of these values. Similarly, with model 2, we do not have a union. Sorry, we do not have true values for both F and G. This before we make conclusion, let's actually also think that was the second part of it. Yes, that was the second part of it, but I want to show this first before we make the final interpretations. So for this one, we see that when I put an enum A, I get a no solution found. We'll investigate this very soon, but I wanted to sort of explain what enums are. And enums, essentially, if you have a list of objects and if you've got limited objects in it, it's also quite likely that you'll also have named your objects. So in this case, I'm just saying that entity has an object which is A. And this is described over here so if you went to learn and then you scroll down to sorts, under the next section of Logic4Fun, we see that there's a bit of a description about it with examples. So often, especially in logic puzzles, we know not only how many things there are of a given sort, but also their names. In this case, we can enumerate or list them. This can be quite helpful as it guarantees, for instance, that all named things are distinct from each other. Incidentally, it also helps the solver run more efficiently. Yeah, so example would be princess, enum, Aurora, and Esmeralda. And dwarves, we've got a list of dwarves, we've got suitors, where we sort of enumerate cardinality, and we've got servants. So this is an example of how enum works. We're not going to very much specifics, but if you want to have a refresher of how sorts, vocabulary, and constraints works, it's in the learn section of Logic4Fun under the next subsection. So essentially, when we have enum A, we get no solution found. But now if I wanted to add another object, for example, if I wanted to add B, this is really similar to the first case, except a 0 gets replaced by A and 1 gets replaced by B. But let's take one more. Let's go one step further and see what we get. Also for this, again, it's essentially the same as the first example, but essentially you get, we do not have any consensus true. So when F is false, G is true, and when F is true, G is false. Similarly, when F is true, G is false, and when F is false, G is true. So we don't have any true and true. And I think this kind of goes back to the point I was talking over here, that semantic Tableau takes a set of formulae and tells you whether there's no interpretation that makes them all true. So we're looking for all true interpretations. We haven't found one so far. Or maybe we did, but we'll discuss in a minute. Again, this was a bit of an extension that I just wanted to play around with. So essentially, it's pretty much the same where we don't have consensus of true. So we've got false, true, true, false, 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 and again, we've got false, true. Yeah, you see the pattern. There's no true, true. Okay, so back to maybe this. When I hit solve, essentially it's just saying that here are two models, and here are some values, here are some objects, 0 and 1, and these are the model you get. But if I went with enum A, I think this is the syntax. There's no solution found, and that just means that if you think about it from the context or from the perspective of semantic Tableau in the tree diagram, every time there was a contradiction, we closed off a branch. This is very similar. So essentially, there was no solution found given the sort, given we have an entity object A, we've got predicates F and G, and we have these constraints where we have true, true, and false. Something cool to note would be something interesting that I wanted to try was I changed false to true. And now, as you can see, we've got one model where we've got F is true and G is true. So for this model, we have a consensus of true, which just means that the sequence is valid when we have A as, like just A as the object. But I'll change this back to false. And this is why essentially you get no solution, because yeah, that's how semantic Tableau works as well. Now if we wanted to add another, this is getting a bit repetitive, but essentially this is the same. We do not see any, I guess it might be a bit clearer why this sequence is invalid for these for this sort where we've got two objects A and B, and for this vocabulary because we do not have a consensus of true and false, and that also applies to this situation if we do not have any true and true in any of the models. So back to the discussion questions. We've checked out the output and we've discussed and interpreted it. We've also tried out what the outputs for entity enum A and entity enum A and B are like, and what sorts of outputs you receive and what interpretations you can make out of it. Finally, we have also sort of discussed how this would help check whether any single branch that we might have constructed can be verified. Yeah. So essentially each model that you've seen were different branches, and yeah, and we can just compare and see whether there is like a consensus of truth. So if all the predicates in the sequence result in a true, that just means that it's a closed branch. Otherwise, it will mean that it's an open branch. The final comment, and I think this is quite important, is that in propositional logic, Logic4Fun can output all interpretations if the number of solutions is set accordingly. And I'll show how you can do this. But for predicate logic, that's not necessarily the case. Logic4Fun does some isomorphism tests and therefore merges some equivalent solutions. So the way you can change the number of solutions that you can get, just go to settings, number of solutions, I just go with all, time limit, whatever, and then I just hit settings again, hit solve again, and now you get all the models. So this is how you get all of the models. And with this, we come to an end for part 2 of the workshop. Now we'll be sort of doing the last part, which is solving the puzzle, puzzle, which is Parking Bay. We do not have 45 minutes, but yeah, I'll try to solve it in 10 minutes and explain how I converted each of these sentences into constraints in Logic4Fun. In the last section, we're gonna have a look at loss property. We'll try to solve this puzzle using Logic4Fun. The way you can find this puzzle would be you just go to the puzzle section, scroll down to intermediate. This is intermediate. No, sorry, we are not doing loss property. We're doing parking bay. Yeah, so intermediate question 8. Okay. So yeah, so there's a bit of a note over here. This is a very straightforward puzzle. And I would also like to add that this is quite similar. It's sort of similar, like it sort of builds on the Logic4Fun puzzle we did in week 5. It really nicely blends with the loss property one from week 5. I think we did that in week 5. Except we're just using for all and we're using there exists. Yeah, there. Otherwise, it's quite similar. Note that if you use int for the positions, there will be no complete function mapping positions to anything else, so it might be better to use an enum sort for the positions. And we just talked about what enum sorts are for the positions with names such as 1, 2, 3, or first, second, third, and so on. That being said, we can also use int, except we'll be defining a constraint to ensure that we do not have a lot of mapping. We just have limited mappings. So yeah, let's just get started. The question is, 5 vehicles were parked, one behind the other, at the side of a street. For no good reason that I can think of, you have to work out the order in which they stood. The first constraint is the white vehicle. Oh, so there's like a couple things to take note. So as we're reading the puzzle, I also like sort of writing or maybe solving as we go. So we've got 5 vehicles were parked. So vehicles looks like a likely sort, and I'll put that down, vehicle, because I also saw that there were colors. So might be good to write them down as we spot them while reading the question. And there are 5 vehicles, so I would assume there are 5 different colors as well. The white vehicle, so we've got one color, was immediately behind the taxi. We've got one vehicle. And the van was more than one place behind the blue one. So we've got another vehicle, van, and we've got another color, blue. The car was not brown, so we've got a vehicle car. We've got a color brown. Nor was the middle vehicle of the 5. So we know there are 5. Okay, cool. The car was further back than the green vehicle, so we've got another color. And the truck further back again. So there's another color, truck. Neither of them was white. Okay. The vehicle immediately in front of the black one was just behind the bus. That's the last vehicle that we need to consider. The bus was somewhere ahead of the taxi and the van was somewhere ahead of the truck. But we are missing, oh yeah, we were missing the black color, but it was just here. Now our box is all green again. Cool. So now for the vocabulary, we will be defining function. And we'll be defining the relations that we have. The first one that we noticed was the position of the vehicle. And while we could have used enum, we'll be just using int, and all the ints would be different. And the color, because we talk about 2 things. We talk about position because we're saying ahead, immediately behind, middle, further back. So these are all positions. And int would sort of say which vehicle is positioned where. And the color, because we're also talking about color, because there's like a white vehicle and then there's like a green vehicle. So we have another relationship. I think I spelled it right. Yep. So this is gonna be a color, different color. So we've defined our sorts and we've also defined our vocabulary. Now we need to define our constraints. For the constraints, because I used int over here, I need to first state that there are 5 vehicles, so we just need 5 ints. And ideally that would be 1 to 5, not 0. So we use for all vehicles. So V stands for vehicles. Position vehicle should be greater than 0. And position vehicle should be less than 6. This is our 0th constraint because we are defining number of vehicles, available positions. Next thing that we're gonna do would be to look at the first statement and see what kind of constraint we can come up with. The white vehicle, so I can see that we have a color V is equal to white was immediately behind the taxi. So the position of V was behind taxi. Let's just do this one first. So we got this. I'll add a comment later. So we've got for all, for all V for vehicle, if the color of the vehicle is white, that would imply that the position of the vehicle is the position of the taxi plus 1. Okay, so the reason why it is position taxi plus 1, first of all, recall that position is int. Position returns us an int value, so we can add whatever int value plus 1. That should be fine. And color returns us, this COL relationship returns us a color, so we can use equal to match the color with white. So as long as, so for the white car, the position of the car would be behind the taxi because it is 1 after taxi. The second constraint is of the first part, the van was more than 1 place behind the blue one. Very similar pattern. So the van, so for all V, the color, if the color is blue, then the position of the van is, here it says more than 1 place, so it has to be greater than position vehicle plus 1. Essentially, if the color of the vehicle is blue, then it is more than 1 because the greater sign, we're not using equal to here, just using greater, is more than 1, the position of van. That was the first constraint. The second set of constraints would be the car was not brown, nor, okay, let's just quickly get this one done. So not color car equals brown. Okay. And nor was the middle vehicle of the 5. Okay, so again, we're doing for all V, position if the position is, so since we've got 5 cars, the middle car's position would be 3. Essentially, did I get the brackets right? No, I didn't. Yep. So essentially, for all vehicles V, if the position of V is 3, then the color of the color of vehicle V would be brown. So essentially, that's just another way of writing that the middle cars, the middle vehicle's color is brown. The third constraint, the car was further back than the green vehicle. Let's quickly code that. Sorry, the car was further back than the green vehicle. Okay. So we have for all V, color V is green because the car was further back than the green vehicle. So, and further here means it could be 1 position further, or maybe it could be 2 or whatever. Further just means it's just behind. We just don't know by how many positions. By at least 1. The next constraint, the next part of it would be, and the truck further back again. So the position of the truck is greater than the position of the car. The reason why we're talking about truck and car is because it kind of specifically means car, green vehicle behind the car, truck behind it. Neither of them was white. So not color car equals to white, not color truck equals to white. And we have already sort of set up that this one would be green. So yeah, we're good. Except I need to fix my brackets again. Yeah. The fourth constraint would be the vehicle immediately in front of the black one was behind the bus. So essentially, the vehicle in front of the black one was just behind the bus. So the vehicle was essentially in middle of the bus and the van. Oh, sorry. Oh, yeah. So the vehicle in question was behind the bus and in front of the black one. So it was in the middle of these 2 vehicles. We don't know what the black vehicle is, but we know that there's a vehicle in front of it, which is behind the bus. So it's in middle. So definitely not position 1 or position 5. If the color is black, because that's the approach we've been using even here, that would imply position V. This is just another way of saying that it's in the middle. Bracket, yep. And yeah, that should be it for constraint 4. Constraint 5, the bus was somewhere ahead of the taxi and the van was somewhere ahead of the truck. So the position of the bus is less than taxi, and the position of the van is less than truck. That's it. We've considered all 5 constraints, and now we can hit solve. And oh, might have to double check. So I think the 5th one was fine. Oh, yep, I see. Yep. So essentially over here, position of the bus, a position of the vehicle V is 1 behind the bus, but I have written V, so hopefully. Oh, something else is missing. The issue was over here. I forgot to include the not symbol because there was a NOR and I just didn't include that, which is why there was an error. Essentially, it was the same thing, but we just missed this thing. Okay. And that's what we get. So the bus comes first, then comes the car, then comes the taxi, van, truck. The bus is green color, truck brown, car blue, van white, and taxi black. With this, we come to an end for tutorial 6. As always, if you've got questions, comments, concerns, please post them on Waddle. Please work on your assignment. And if you've got questions about that, please post them on the forum as well. And we'll see you week 7. Good luck with your assignment.